know what I mean? Derivative. So this is the derivative of x to the fifth, which means the limit is 5x to the fourth. Done. If you have an actual number here, so instead of like x plus h, it's 7 plus h minus 7 to the fifth, then you would get the derivative and then plug in 7 and see what you get. Over here, this is the derivative of what? Of sine x. The derivative of sine x is cosine x. You're done. Again, if you see an actual number here for x, so instead of sine of x plus h, it's sine of like pi over 2 plus h, then you get the derivative and plug in pi over 2. So that's all. Again, you'll have a few multiple choice questions along these lines, like what you saw here and what you saw yesterday. This one's a little more subtle because in this one, they're embedding the function into the limit. So you have to look a little bit more closely and say, oh, the function is right there, x to the fifth. And that's what you differentiate, as opposed to yesterday where we just kind of gave you the general limit and put the function off over here and said, this is the function for f of x plus h minus f of x. So here it's a little more subtle, but you guys get the idea. And I think next week we'll just keep doing warm-ups where I just rip stuff from the final. We got one last day of stuff where we're doing, stuff. So yesterday we started looking at your first derivative test. Hi, Iman. And we're using the first derivative test to find relative extrema. So I want to finish off the example we started yesterday and then work through 2 more examples with different types of functions. And at that point, we'll have done an example with a...
Pardon the interruption, I'm looking for John Cacciatano. Mr. Cacciatano here. Needed in coverage. You needed 19 for coverage. With 19 for coverage. It's John Cacciatano, thanks.
We need less coverages if everybody else would just show up and do their jobs every day. Anyway, so so yesterday we looked at a polynomial example and we started a trig example, and then we'll look at 2 more where we have like a radical fraction exponent example and a fraction function. So yesterday, remember, to do your relative extrema, you start off, find your derivative, set it equal to 0, see when it's undefined to get your critical numbers. Once you have your critical numbers, you use them to break up the domain. In this case, it's just from 0 to 2 pi, into little sections, call them subintervals. And then once you've got that table of intervals, you plug a value from within each interval to the derivative. And if the derivative's positive, you know your function's increasing. And if the derivative's negative, your function's decreasing. And then you can kind of make a conclusion from there on whether you have a maximum or a minimum or neither at each of your critical points. So yesterday we got up to this point where we got the derivative, we got the critical numbers, we set this up. I think we picked numbers to go in. So between 0 and pi over 3 is pi over 6. And maybe it's helpful to like have a quick little unit circle here. So here's 0, and then pi over, what's this angle? 6, and then halfway through the interval is pi over 4, and then up here is pi over, and then up top is pi over, and then halfway round is, and then down here is 3 pi over 2. And then I don't normally fill anything into quadrant 4, but in this case I will, because we have a critical number at 5 pi over 3. The 5 pi over 3 is just the quadrant 4 version of pi over 3, so that's down here. And I think a good, not 12, this is 6. A good value here would be 11 pi over 6, between 5 pi over 3 and 2 pi. So I'm going to choose pi over 6 between 0 and pi over 3. I'm going to choose pi between pi over 3 and 5 pi over 3. And I'm going to choose pi over 6 between pi over 3 and 2 pi. And I'm going to plug each of these back into the derivative to see is the derivative positive or negative. So for pi over 6, so this is 1 comma 0. What are the coordinates here? Root 3 over 2 comma 1/2. For pi over 3, it's 1/2 comma root 3 over 2. For 5 pi over 3, we'll just use the pi over 3 coordinates. And then for 11 pi over 6, we'll just use the pi over 6 coordinates. And for pi, it is -1 and then 0. And cosine is going to have us look at the x coordinate associated with each angle. So for when we do pi over 6, that's going to be 1/2 minus, what's cosine of pi over 6? Root 3 over 2. And is that going to be positive or negative? Negative, because root 3 is bigger than 1. So when you subtract root 3 from 1, you get a negative. So that's negative, and so that means f is decreasing. Then for pi, what's cosine of pi? -1. So we'd have 1/2 minus -1, so +1. And that's going to be greater than 0, so that means f is increasing. And then for 11 pi over 6, we're in quadrant 4. Is cosine positive or negative in quadrant 4? Positive. So you just look at pi over 6 and keep it positive. What's cosine of pi over 6? Root 3 over 2 again. So that's back to 1/2 minus root 3 over 2, and that's negative again. So f is back to decreasing. So that is, hey, if you want to find out where's the function increasing and decreasing, that's your process, and you can stop right there. And you'll have a couple of questions like that on the final exam, where all you need is the intervals where we're increasing or decreasing, and probably those problems will not be with trig functions. Any questions up to that point? Yes. What percent is this stuff of chapter 3? Well, there are, this is the final. So there's 2 pages of free response, and there's 1, 2, 3, 4, 5 problems there. And then there's 35 multiple choice questions. I know, I'm just telling you. So, of chapter 3 stuff, 1 of the free response problems, similar to this right here, of find your critical numbers and find where the curve is increasing and decreasing. And then of the multiple choice stuff, there is no. 1, 2, 3, this was the version that I just printed out of the printer to make sure that everything worked out before I ran off copies. 3. So I think there's 3, maybe 4, if I missed one, multiple choice questions dealing with chapter 3 stuff. So 3 multiple choice, or maybe 4 multiple choice, and 1 free response question from chapter 3. 5 free response and 35 multiple choice. Now the 5 free response, one of them includes parts A, B, C, and D. Yeah. So it's more like 40-ish. Between 35 and 40, depending on how you count. What? So how do I know which coordinate to use? Or, oh, like how did I know to add here? Because cosine of pi is -1, and 1/2 minus -1 is really +1. For here, root 3 over 2 and root 3 over 2, cosine of pi over 6 is just root 3 over 2, so I'm just subtracting root 3 over 2. And 11 pi over 6 is quadrant 4. Cosine's positive there, so it's also just a regular root 3 over 2 that I'm subtracting. Any other comments with that? So now, in this problem, we don't want to just get the increasing and decreasing intervals. We also want to find the maxima and minimum. So we kind of extend this little table and draw some conclusions. So since our function is decreasing and then increasing, right at this point, pi over 3, do we have a max or a min? So curve is decreasing and then increasing. So a minimum, because you're going down and then you're going up. So that's going to be a minimum. And then here, you go from increasing to decreasing. So that means at x equals 5 pi over 3, do we have a max or a min? Max, because if you're increasing and then decreasing, you're going up and then you're going down. So right there at the top, you have a maximum. And to find out what they are, plug them back into the original function to get your y's. So for your minimum, you would say do y equals f of pi over 3, and that's 1/2 times pi over 3 minus the sine of pi over 3. I should not have erased my unit circle. So 1/2 times pi over 3 is pi over 6. And what's sine of pi over 3? Root 3 over 2. So that is your actual minimum value. And it's at the point pi over 3 comma this ugly thing. And for the maximum, you do the same thing. Y equals f of 5 pi over 3. So you have 1/2 times 5 pi over 3 minus the sine of 5 pi over 3. So 1/2 times 5 pi over 3 is 5 pi over 6. And then what's sine of 5 pi over 3? Well, what was sine of pi over 3? There's root 3 over 2. What quadrant is 5 pi over 3 in? A sine positive or negative in quadrant 4? Negative. So we're going to be subtracting a negative. That's really going to be a plus root 3 over 2. So there's your y coordinate. That's your maximum. So now we're all finished. If you wanted to find the absolute maximum on the interval and the absolute minimum, you'd also plug 0 and 2 pi to check your endpoints. But if you only want the relative max and min, you stop there because relative maxes and mins only happen in critical numbers and we don't care about the endpoints. Follow up with this one. All right, example 3. What's your first step? Derivative. Great, do it. You find the derivative. To find the derivative, what rule are you using? Chain rule. All right, so do your chain rule, get the derivative for that thing. Yes. Yeah, so you use that switch from one. So that's where we switch from so that's where we have. All right, so step 1, you get your derivative. What is it? So 4x over 3 times x squared minus 4 to the 1/3. There will be a number of problems on the final where it's going to be just, here's a function, show me you know how to get a derivative. I can go through next week and kind of go through and kind of break down how many of this type, how many of that type of like like I did with chapter 3, you have 4 or 5 problems dealing with chapter 3. So next week, maybe I'll go through and say, how many problems is it just, here's a function, just get the derivative. Just to know, do you know your derivative rules? Do you know your trig derivatives, and your chain rule and product rule and quotient rule and so on? Any questions with getting that? So now, step 2, you get your critical numbers. And remember, critical numbers are numbers that do what to your derivative? Make it 0 or undefined. So for f prime of x equals 0, what's that going to be your solution for x? 0. So you set this thing all equal to 0, and you multiply the denominator over. 0 kills it, and you're left with 4x equals 0. For your derivative being undefined, what has to happen for your derivative to be undefined? Yeah, then the denominator is 0. And that's going to happen for what x values? Yeah, positive or negative 2. Yes, Ryan?
So what if you get imaginary numbers in the denominator?
Like if you get, say it's x squared plus 4, right?
Or like, if you put 1 in for x.
Oh, I see what you're saying. That would be fine because this is a cube root. So you would not get an imaginary number. You can cube root negatives just as well as positives. If it were a square root, yeah, I'd see. That would be an issue.
Are they critical numbers?
Technically, because it makes the derivative undefined, but it's just like not even in the domain of the function then. Because if this is a square root down here, it must have been some sort of even root originally. And so that number would not have been, that would be something that's like kind of cut out of the domain anyway. So it's not going to be a point on the graph at all. That's a kind of subtle little nuance to worry about if it ever happens, but it probably won't. So you have your critical numbers here. 0 makes it 0, plus and minus 2 make our function undefined. So probably these are points that give us like sharp turns in the graph. So now we go ahead and do our table. So have our intervals. So what's our first interval going to be from? Start out on the very left. Yep, when in doubt, and they don't give you a specific interval like they did in the previous problems, just assume starting out at negative infinity. And then you're going to go until you get to, nope, negative 2. And then negative 2 to 0. And then 0 to 2. And then 2 to infinity. So the more critical numbers you have, the worse your life gets because you have more intervals to check. Now, and then you got to check all of them. So how about if you're a guy, check the 2 left intervals, and if you're a girl, check the 2 right intervals. So guys, check negative 3 and negative 1 back into the derivative. Girls, check positive 1 and positive 3. And again, we don't care about the value. We care about is it positive or negative. So you might be able to kind of reason it through and think, well, the numerator, what's that going to be? Positive or negative? Denominator, is that going to be positive or negative? That's really all you care about. All right, so any guys, f prime of negative 3, is it positive or negative? Negative? I can buy that. So I guess negative 3 squared is 9, minus 4 is 5. So you have a positive down here and a negative up top. So that's negative. And any guys for negative 1, positive or negative? Positive. Can I have a negative over a negative? Girls, for positive 1, is your derivative positive or negative? think it's negative because now it's a positive or a negative. And then for x equals 3, positive or negative derivative. I think positive because now it's positive over positive. So f is decreasing, then increasing, then decreasing, then increasing. So at this first switch of intervals, that happens at x equals -2, do we have a min or a max? Min. So that's a min at x equals -2. So we can come up here and we say x equals negative. Why do I keep forgetting the negative? X equals -2. And then from the second to the third interval, that happens at 0. And we have a max or a min there. A max, because we go from going up to going down. So max at x equals 0. And then from the third to the fourth intervals, we have a min again. So we have 2 minima and 1 maxima. So minimums happen at -2 and +2, maximum happens at 0. And then that's not what the minimum and the maximum are. Those are just where they happen. So maybe I should write at. The actual minimum, the actual maximum is the y-coordinate. So you would take these and plug it in and say, all right, y equals f of -2. When we plug -2 in, what do we get back? 0. And for y equals f of +2, you plug in +2, and what do we get back? I think also 0. So your minimums as points are -2, 0, and +2, 0. For the maximum, you plug in 0, and what do you get? And it's allowed to be ugly. All right, if you don't want to make it a decimal, that's okay. Ryan? Cube root of 16.
That also equals to cube root of 7.
It is, well, 16. Anybody want to go through the process to get here? You guys see that? Okay, so, yeah, perfect cube that goes into 16 is 8. So you could break that up like this. And so this is 2 cube roots of 2. Yeah, so if you plug in 0, you're left with -4 to the 2/3. -4 squared is 16. And the 1/3 power is the same as a cube root. So that's how I was getting the cube root of 16. You could reduce it to that. You could leave it as cube root of 16, and nobody's going to come and burn your house down over it. You could make it a decimal, and that would be 2 point something. I don't know. So say this is 0, 2 cube root 2 as your max. Ta-da! That's it. And probably these are absolute minimums, and then this is just a relative. Well, let's try to graph this. Try to put this together. You have a point at -2, 0, +2, 0, and then 0, 2 cube root 2. So I'll put that there. So this is a minimum, and it's gonna be a sharp turn because that's when the derivative's undefined. So the curve is decreasing. Hit there. You bounce off of it. You hit a maximum. You hit there. You bounce off of it with a sharp turn, and then you're like that. So if you graph this, it's probably what it would look like more or less. And you can kind of put this together between, hey, we're decreasing on the left, so we're coming down until we hit that point, and that's a minimum, so we have to start going back up. We hit this point here, it's a maximum, we have to start going back down. This is a minimum, we have to start going back up. We're increasing all the way out on the right, so that works. And so it kind of fits with your points and your tables. Questions to follow that up? So this is like you're finally able to graph things with precise maxima and minimum points and increasing and decreasing all the places you're supposed to be. without having to do any reliance on the calculator. You're able to do it all by hand. So congratulations, we've graduated into the 1700s, mathematically speaking. All right, one last one, and then I'll appreciate you a little bit and call it a day. Not force more math down your throat. Because at that point, we'll have covered exactly the same amount that I covered last year in this course, and my AP kids this year did okay with where we started, picking up where we left off last year, so I think we'll be fine. Laura. So next week, you come in, warm up, go over homework 3.3, review. And I'm thinking review could be whiteboards. I look at the final exam, and then I make up a problem like what I'm seeing on the final exam, and you do whiteboards. Or maybe better, it's not whiteboards, it's Twitter, write in your notes, because then you can refer to it later. And then on your own time at home, I'll give you a laundry list of problems from the textbook. You have that extra credit Delta Math thing that you can do. And I want your textbooks back before or on the final exam. So I don't have to run and chase people down and do obligations and all that, because that's not going to matter. So either bring it in and leave it there. Yes. So the homework assignment that's on School with You for tonight is your last homework assignment for this class. No. Excuse me. I'm not going to make that due 3 days before the final. So that's due on the day of your final. So
What time Friday?
your finals Friday at 7:30. I'll have that up there right next week. Yeah, I know. Like all year. Yeah, come in, guys, at 9:45 or 11 or whatever your first class of the day is. Final exam 7:30. They didn't ask me. Bryson. Would you like one? Okay, done. George,
On Friday, the bus leaves us.
say that what?
Friday.
Yeah, what about it?
The bus leaves us.
Are you going to get a bus on Friday? I certainly hope so. I won't be driving it, I don't know. I assume that the bus drivers know that next Friday is a different schedule for all. Otherwise, you can just take a 0 on the finals. I don't care, it's not my group. So, what? It's not the rudest thing I've said today. Am I recording? Yes.
That was not me. Definitely work.
Oh, absolutely. But you say it with a smile. Everybody's smiling. It's like, oh, he's smiling. He's saying a nice thing.
Anyways, back to math.
Back to math before I do say something stupid. Step 1, derivative. Now, you have options on this derivative. Option A, quotient rule. Option B, what does this mean? It means rake it apart. Like Ryan, Ryan was I was just giving a sound effect for Ryan's action. So I would recommend option blah, but if you want to do quotient rule, it's fine. So go ahead and get your derivative, and then start working on your critical values. So option 1, step 1, f prime of x equals, figure that out. Do they look like they're having fun out there?
There's a lot of talk.
A lot of talking? Well, that's a good sign. At least they're not all looking at their phones.
Giant.
You look out the. You look out your window to the back.
It's the courtyard. when I had a class down the hall, and I think 306, it overlooks the bridge to the courtyard. So we spent a lockdown trying to throw paper airplanes out of the window and get them to land on the bridge. It was a fun day. Harnor. That's going to be an actual question in a couple of years. Do you know where the cafeteria is? No, actually, I don't. We're not allowed to eat there.
What is that?
The derivative?
Yeah.
Yeah.
Okay.
I know. I mean, we're on
So that was the issue. All right, so what's our derivative? Do we need to work through the derivative? So do you want to do quotient rule or blah? Blah. All right, so blah is x to the fourth over x squared plus 1 over x squared, right? And then you reduce things and make it more friendly for derivatives. What's x to the fourth over x squared the same as? X squared. And what's 1 over the x squared the same as? 1x squared to the negative 2. And then that'll probably be easier to differentiate than doing quotient rule. So if I were me, this is the method I would take. But if you were you and you like to do quotient rule, then that's fine. So derivative, using the blah method, you get 2x minus 2x to the negative 3. And then you can throw some stuff down the stairs to make it have a positive exponent. And there's your derivative. If you want to put things back together so they have a common denominator, especially this, you can do that, but I don't think it's super necessary. Yes? So you got 2x to the fifth minus 2x. All right. And then what can you do to that? You've got an x, so you have 2x to the fourth minus 2 over x to the third. Guess what would happen if we got these back together? The same thing. So common denominator is x to the third, right? Multiply this by x to the third, you get 2x to the fourth, minus 2 over x. So it's the same thing. So, you know what? Actually, I think I like this version better to then work with. So we'll use this. So f prime of x equals 2x to the fourth minus 2 over x cubed, once you put things back together, or if you do your quotient rule and reduce it. And I like this better because it's easier, I think, to solve for when it's equal to 0. So what are our critical numbers? How about for when f prime is undefined? I feel like that's going to be easier here. 0. So f prime undefined, oh, that's x equals 0. For f prime equals 0, that's a little more work. What part of this really equals 0 then? Numerator, 2x to the fourth minus 2 equals 0. What can you do to that? I would probably factor out a 2. And then factor, what does x to the fourth factor down to? X squared plus 1 and x squared minus 1. What does x squared minus 1 factor down to? We got x plus 1 and x minus 1. Why did I not bother doing anything with the x squared plus 1? It'll giving me imaginary crap, but I don't care about imaginary things. Anyway, so we get plus and minus 1, not just positive 1. So that's why I like factoring. It kind of makes clear, oh, there's a negative option too, where if you do the whole add 2, divide by 2, take the fourth root, you might forget the negative option. So you have all your critical numbers. So you get your derivative, either with quotient rule or breaking it apart and differentiating separate terms. Set your derivative equal to 0 and solve. You see when is the derivative undefined, and you have your critical numbers. And now you can intervals. Where does our first interval begin? And it goes until, and then from -1 until, and then from 0 until, and then from 1 until, Yeah, a little bit. Now, I think what's especially gross is that you're going to have to use fractions or decimals in here for a couple of examples. F prime, pick a number between minus infinity and minus 1. -2 or 200, whatever makes you happy. So, checking your derivative. -2 to the 4th is positive. -2 is still going to be positive. So positive on top. -2 cubed is, so we have a positive over a negative. That's usually negative. So F is decreasing. What do you want to check between -1 and 0? 1/2 seems reasonable, so F prime of -1/2. -1/2 to the 4th. Positive what? A number. 1/16. Because 2 to the 4th is 16, so 1/2 to the 4th is 1/16. 2 times a 16th, 1/8. -2 is negative. -1/2 cubed is negative. So negative over a negative is positive. So this is the sort of thinking you should be doing with your derivatives. You don't really care about the value, you just care if it's positive or negative. F prime of positive 1/2. Is the top going to be positive or negative? Negative. Is the bottom going to be positive or negative? Positive, because now it's a positive 1/2 cubed. So that's going to be a negative over a positive is negative. So F is back to decreasing. And then, last interval, 2 or 200. F prime of 2 on top is, on the bottom is, so it's positive. So that's F increasing again. So once you kind of get through this a couple times and you see what's going on, is it super difficult? No. Nah, I mean, there might be aspects of it that are more or less difficult, like maybe finding the derivative is a little tough, because you have to do chain rule, or quotient rule, or mess with that. Maybe solving is a little bit of clever algebra. But there's all things you know how to do. Like, you know how to find a derivative now. You know how to solve an equation when it's equal to 0. You maybe have to think a little bit to do that, but you can do it. You've been doing it for years now. This is super tedious, like plugging in a number to an equation and seeing is it plus or minus. It's tedious, but it's not like the worst thing ever. You've done tougher things than this. It's just what's tough about it is it's so long. Like, one problem takes up a whole board here. It's a lot to just keep track of. So there's lots of opportunities to screw something up along the way. So you just got to really commit yourself to focusing on detail throughout and not losing focus halfway through. All right, so we're getting near the end here. At -1, max or min or neither? Min. At 0, max or min or neither? Max. Maybe, we'll come back to that. At this last one, max or min or neither? Min. To find out the actual point, take these and do what? Plug into that actual function. So y equals f of -1. Back to the beginning. What's -1 to the 4th? 1 plus 1 is 2 over 1 is 2. So we have the point -1 comma 2. So the max is actually not there. Because if you plug in 0, it makes 0 in the denominator. So this is what's the numerator? 1 over 0. Okay, now, last from the past, go back to your limits. What happens in a graph if you're getting 1 divided by 0? That's a vertical asymptote. So instead of a actual maximum, we really have a vertical asymptote going on there. So there isn't really a point. What's going on is the curve is going up, a vertical asymptote. There's a vertical asymptote at 0, and then on the other side, you're coming back down out of the heavens graphically. So first derivative test makes you think there's a maximum, but then really there's not. There's a vertical asymptote instead. So back up here is like, just kidding. Okay. Minimum f of 1 is 2 again. We have 1 comma 2. So if we were to graph this, we have actually a vertical asymptote at 0. We have a point at negative 1 comma 2. We have a point at positive 1 comma 2. And we would say we are decreasing and then increasing. So decreasing and then increasing, and then we're blocked off by the vertical asymptote. And then coming out of the vertical asymptote, we're decreasing, hit this point, and then we're increasing again. So it's going to be like that, more or less. Ta-da! What are we out of here? 45? Awesome. I will appreciate you for 5 minutes. Here is final exam review stuff. So on the first page is just stuff I recommend you look at, notes, Delta Math, old quizzes and tests. I've posted a version of each quiz and test we've done since we started limits on Schoology. You can't see it yet. It's in next week's folder. And then a bunch of problems from the textbook that you can look at if you have really no life. And then the second and third pages is kind of like a very big picture summary of stuff we've looked at and things to pay attention to. And at the end is when your final exam is. I hope that's information is correct. So here we go. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, 121, 122, 123, 124,